my outline very briefly. We'll talk about the background on the Rabi-analogue splitting, which is the main phenomenon we're going to discuss here, and then we move on to the plasmonic hybrid device with an active medium, and look at the experimental result and the theoretical results and the conclusion. Now, initially when we started back in fact 2013, we have this design a plasmonic hybrid device in which in fact we have a 2D array, square array of silver. Then we have a microcavity, and between the microcavity and the 2D array of silver we have 30 nanometers of silver, which basically provide the microcavity confinement, as well as thin enough that the SPP mode, the surface plasmon mode, polariton mode, can couple with the microcavity modes here. The B here is the SEM, seeing that from the top. The thickness here is all shown here. We have a periodicity of 320 nanometers, and the dimension of each of these pillars really is 160 by 160 nanometers with a height of 15 nanometers. And what we summarizing very briefly the result, what we have seen here on the right hand side is a simulation of the TM modes and the experimental on the left hand side. You can see here we have the SPP modes and then the cavity modes at when they are having the mode coupling. You see an anti-crossing here, and that's both in experimental and simulation. You will see that they are very closely agreed to each other. If you look at the further analysis of that, is that the coupling here basically creating a quasi-particle, or which you have a mix of cavity and surface plasmon polariton energy exchange. And this is very similar to the Rabi splitting. However, Rabi splitting itself is a quantum phenomenon, whereas here it's basically a classical phenomenon. Hence the term Rabi-analogue and not strictly Rabi splitting. The difference here in terms of the wavelength is about 30 nanometers, and that's corresponding to, in fact, an energy difference of 148 MeV, which is a fairly large splitting. So this is entirely due to the fact that the SPP mode will be able to couple into the microcavity, and what we can see here is the mode coupling between the cavity modes and the SPP mode. And here you can see we use this is the Hamiltonian, in which we will look at the calculator, looking at the theory of it, and a little bit more detail. You can have a plus and minus of the split of the energy to give you that energy splits here. Now with that, what we have done at that time, I might just go back very quickly here. Here is that the dielectric we use here is silicon dioxide, 120 nanometers, and strictly is a passive medium. So what we have done, we move on to having a bigger bigger area, nanostructure, in which we use the laser interference here to cause the interference, increase the change in the periodicity. The laser use is 442 nanometers, and reproducing it so that we can actually have a larger area for measurement, and the silver depositing on the photoresist is about 30 nanometers. Now the area is quite large. It's about 1 by 1 centimeter square. Oh no, sorry, it's 0.1. So it's 10 by 10 millimeter square. So this is the interference. Using the interference, we can have a different periodicity that give us a much quicker way of making this grading, although it's one-dimensional, but we can change it from 354 to 410 nanometers periodicity. So give us a certain amount of flexibility as well as a larger area for measurement. So now we switch to, instead of using silicon dioxide, we use in fact PMMA. Here is a 500 nanometers of PMMA as a passive dielectric, and the rest of that is relatively similar. And what we have seen here as a passive matrix is that we see anti-crossing at around about 49 degrees incident, and at a wavelength of 750 nanometers. And we're sweeping from 47 degrees all the way to 61 degrees. You split the graph here because otherwise it's get very complicated and too complex to look at. And this is at about 49 degrees that we see the maximum split. The split is not large, it's only 78 MeV, and that's corresponding to a delta lambda of 32 nanometer. After we have done that and confirmed the fact that we indeed can see the mode coupling and we can see the Rabi-analogue splitting, then we introduce an active medium, and we're using a dye, small molecule dye called EY51, which is very similar to the Rubrene. What we have done here is, schematically you can see, is that we introduced a layer of EY51 and then top it up with the PMMA, and the total thickness here remain constant. So by changing the thickness of the EY51, we can actually change the luminance intensity of the EY51. Excitation comes from the bottom through the glass, and the light actually we use here is to generate the SPP as well as, in fact, excite the EY51. Hence, the EY51 is very close to the grating itself. And then the rest will be blocked and absorbed by the PMMA, which actually doesn't play any part in the active mode coupling. The grating size, everything is tuned slightly to match with the emission of the EY51. So the pitch size for the grating is 360 nanometers, and that is for the grating, and the height is 20 nanometers. The silver here is top here is the bottom here is 45, top here is 120 nanometers. Now for the Rubrene EY51, we have in fact a peak of the photoluminescence around about just longer than 550 nanometers, and our in fact grating here now is a resonant peak at that. So that gives us in fact a matching in terms of the resonant coupling. So 560 nanometers, we can see that, that's yellow color. And here we can see that if we have no grating at all, which is the red line on the left, here the PL is broad across anything from about 460 to just about 650 here. But if you added the grating in there, you can see a strong enhancement of the photoluminescence. That means that there is in fact a coupling effect between the grating and the active medium. The right hand side here just merely show you the pure EY51 film luminescent properties, which should have a peak around here, which is 560. So we do see there is an enhancement, and so the microcavity here gives you a much broader, in fact, luminescent. Basically, the luminescent here gives you a much broader here. So coupling with that, what we have done is we use the thickness of the, having a series of thickness of the EY51 film that give you, in fact, different luminescence intensity coming out from the EY51 film. And the thickness of the PMMA is adjusted overall to match with the constant thickness. Here we can see from A, B to C. A here, we see the actual gap here is at 630 nanometers. The split of the Rabi-analogue split is 240 nanometers. And when you increase the EY51 film to 50 nanometers, that means you increase the photoluminescent intensity. The gap here now has, in fact, slightly blue shift to 600 nanometers, and the split itself is enlarged to 280 nanometers, MeV, sorry. And however, if you increase further on the EY51 film to 80 nanometers, the gap actually rate shifted back to 670 nanometers, and we observe no split at all. So basically, you will see that in fact you have an optimum in terms of the contribution of the luminance from the EY51, and that optimum is actually placed at 50 nanometers, which is a B. And one can see here is that there is a narrowing and deepening of the gap here, the lower dropping of the reflectivity. And so once you pass that and you increase the thickness again of the EY51, then the whole thing in fact broaden up again, and in fact there's no more split you can see. So there is in fact not a continuous increase in the coupling and the split, and therefore the splitting of the because of the more coupling. However, in fact there is basically an optimum in terms of the additional luminance involvement into the more coupling. So that's the experimental results. So we move to looking at the theoretical side, how we can look at that and try to explain through that. We use a similar Hamiltonian, and based on in fact the parity times symmetry approach. Here, the omega here is the resonant frequency of the cavity and the SPP. Gamma is the loss of the cavity and the SPP, and G is the mode coupling itself. And if we can get the resonant frequency of the couple modes by diagonalizing the Hamiltonian, and that will be the equation we have here, where A is this, where you have the delta omega and delta gamma, and B again also in terms of delta gamma and delta omega, where delta gamma is the difference of the loss of the cavity to the SPP, and delta gamma is the difference of the resonant frequency of the cavity and the SPP. So very much is governed by here the A and B. Now at the mode coupling, which we can go back to here, you could see, in fact, if I could very quickly do this one, is give you a much better idea, is that because at the mode coupling they are crossover, and therefore both the SPP resonance frequency and the cavity mode frequency is the same. So the omega is the same. So if we go back to here, it's because the two frequencies is the same, and therefore then delta omega is 0. So we are saying we call that simply as omega r, and therefore in this case the B in this equation will be 0, and in A this is 0, delta omega is 0, and A therefore now is being reduced to simply as 4g squared minus delta omega squared. And at the resonance here, at the coupling point where it's resonant, in fact, we basically means that in fact we will have a very large split. That means the contribution from the delta omega here should be minimum. So we can in fact assume that the G will be much bigger than delta omega here. In that case, we can approximate the square root of A is approximately equals to 2G. So if you substitute back into the equation, here, and simplify it, you can get this term here. And this term here, you could see now is that purely now, in the real term here, will be the resonant frequency plus or minus G. So that actually gives you the split itself here. The other one is in fact the loss itself. So since G in fact is the largest, and therefore we basically, you could say here in fact is that the resonant frequency split is at its maximum, and this is what we have seen. So quantitatively we can actually see from here is that at a certain at the resonant you will get a maximum, but outside the resonant, beyond, before you approach the resonant on the mode coupling point and out away from the mode coupling point, in fact the split will drop very much. The other parameter we can look at is in fact is the resonant line width, and gamma. Gamma is defined as the real of the plus and minus resonant frequency real part divided by the imaginary part, or the sum of the imaginary part, which basically sum up to here. And the top part here will be summarized here. We know B is 0, and therefore this can be very quickly simplified to this term here, as the gamma now is equals to square root of 8G divided by the sum of the two loss. Now G itself, which is the modal coupling, as well as the loss of the SPP, we can assume it to be really a constant. They are really a constant within a coupled system, as we are not changing anything at all. Whereas the loss of the cavity would change because of the contribution of the active medium, and therefore the loss of the cavity could be reduced and reduced to could be approached to gamma of the SPP, the loss, and even approach to 0. So basically we are saying here is in fact the photoluminescence of the EY, the luminescence here, is compensating the loss of the cavity, which in fact by doing so, therefore we can assume that at least at the coupling point the loss of gamma cavity here will be at its minimum, and therefore this is minimum by reducing the denominator, and therefore your line width here will be at its so-called maximum. That's the split of that, the ratio of the split. Again, this is seen in the experiment. In fact, we can look at the line width itself here and look at the narrow rate, taking to example the maximum line width, the splits of Rabi split here is 218 MeV. We're looking at the resonant, which is this part of that. The resonant line width here is 13 nanometers, whereas if you look at no split, which is using 18 nanometers, the line width actually has brought them back to 17 nanometers. So there is in fact by percentage, there is in fact a significant narrowing of the line width, and that's due to the fact of the compensation from the luminescence of the EY51 here are reducing the loss of the microcavity. So in fact, what we have also done in our work here is to look at the device here and looking at the loss and looking at, in fact, by a broader term, and looking whether, in fact, we can see the exceptional points. If it does actually conform to the characteristic of the parity time symmetry, then we should be able to see the presence of the exceptional point, EP. And indeed, we can see that at a certain parameter where the gradient is 20 nanometers, where the silver thickness has 20 nanometers, we can see there's a couple of cavity modes and the SPP mode. Here we can see, in fact, two possible exceptional points at 30 degrees, 30 odd, and 54 degrees. 54 degrees. So that basically means that this is a theoretical experiment, as theoretical simulation. Here we have, in fact, in this simulation, in fact, our Hamiltonian becomes a little more complex. We are looking at not only the zero mode, we are looking at higher modes of the SPP, and they are coupling to the cavity modes. And G here now becomes the loss plus the pumping here, which we can tell as the reducing here. The loss here is we put it down as 0.01, quite low, but you can see that the presence of exceptional points is quite obvious. This is ongoing work at the moment, and what we want to do is to be able to come up with a design whereby we can actually doing a photo work and experimentally and quantitatively be able to show that we can observe the exceptional points. So in summary is that we have fabricated and designed a hybrid plasmonic device, and showing that it is, in fact, we can see strong cavity and SPP mode coupling, and we have a strong Rabi-analogue splitting. And this complex coupling here, it can give you, in fact, a very good possible application, and by tuning basically the two parameters between the SPP and the microcavity, you can basically design where you want to do the mode coupling. And then we introduce we introduce an active medium into the dielectric there, and that acting as a loss compensation component. In so doing, we can see we have an enhancement of the Rabi-analogue splitting from 78 MeV to 280 MeV, as compared to the most earlier work, which have a reasonably large split of 148, that we can even improve upon that to 280 MeV. And theoretically, we use the PT symmetry approach, and we can show, in fact, qualitatively here, our experimental work can be explained in terms of the narrowing of the full wave half maximum, as well as the split of the Rabi-analogue due to the compensation effect from the input from the photoluminescence of the active medium. And we done further simulation work to show that there exists a possible two exceptional points by tuning, in fact, some of the parameters, and we have, in fact, started working on the experimental to prove experimentally the presence of the exceptional points. And finally, the work is supported by the Research Council, Grant Council of Hong Kong, under these two projects, the AOE and the GRF grant. And